Now let's look at what happens when we need to change variables with a definite integral. Everything is the exact same, except you need to change your upper and lower limits. Because remember, the upper and lower limits have to do with the function that you're integrating. So to find g at a, after you identify g of x equals whatever that is, you're going to come down and you're going to evaluate g at the lower limit, and you're going to replace this as your lower limit. Then you're going to evaluate g at the upper limit, and this becomes your upper limit. Now, the beauty of this is you do the u substitution, but unlike indefinite integrals, you do not ever have to go back to x. Because remember, a definite integral gives you a number, it gives you an area. So let's try one. Suppose we have the integral from 0 to 1 of x times x squared plus 1 quantity cubed dx. Let's let u equal x squared plus 1, then du is 2x dx. I have x dx in my integral, so I'm going to solve this for x dx. That is du over 2. Now I need to come in and change my variables. U, evaluated at 0, is 0 squared plus 1, or 1. U, evaluated at 1, is equal to 1 squared plus 1, or 2. So we're going to wind up plugging these in as our upper and lower limits in a minute. Now, let's substitute all of this in. It becomes the integral from 1 to 2 of, now x squared plus 1 cubed is u cubed, and x dx is du divided by 2. So this becomes u raised to the power by 1 to the 4th divided by 8, evaluated at 1 and 2. So now this is 1/8 times 2 to the 4th minus 1 to the 4th. So this is 1/8 times 2 to the 4th is what, 16 minus 1. So this is 15/8. Now, here's another change of variables that you need to pay careful attention to. Suppose I'm looking in the interval from 1 to 5 of x divided by the square root of 2x minus 1 dx. To evaluate this integral, let's let u equal this entire square root. All right, so now let me do a little massaging here. U squared then is 2x minus 1. So x, I'm just going to solve this for x, is u squared plus 1 over 2. Now I'm going to differentiate each side. When I do that, I get dx is equal to, let's see, this becomes 2u to the first du, and then plus 0, and this is all over 2. I could have written this as u squared over 2 plus 1/2, and when I took the derivative, that goes away. So dx becomes u du. All right, so now I need to come up and find my limits of integration. U of 1 is the square root of 2 minus 1, or 1. U of 5 is the square root. 2 times 5 is 10 minus 1, which is the square root of 9, which is 3. Now let's see what happens when we plug all of this into our integral. It becomes the integral from my lower limit is 1, My upper limit is 3. The integral from 1 to 3. Now, let's see. This becomes, when I do all of this substitution, I've got x, and x is u squared plus 1 over 2. So this is x, which is, whoops, I wanted a u, not an x, getting carried away there. U squared plus 1 over 2, that's my x term. Now I've got 1 over the square root of 2x minus 1, so this is 1 over u. And then for dx, I found that dx is u du. So you see how I broke it up into the 3 sections and slowly plugged them in. Now, I can't integrate this as is. I need to do some simplification. That u is going to go away. I can factor the 1/2 out. So this becomes 1/2 the integral from 1 to 3, excuse me, of u squared plus 1 du. Now this is a straightforward integral. So this is 1/2 times, this is going to be u cubed over 3 plus u, all evaluated at 1 and 3. So this is 1/2 times. Now I'm going to do this first one in green. U cubed over 3 evaluated at 1 and 3. I'm going to factor the 1/3 out. So this is 3 cubed minus 1 cubed. So that's my first term. And now I'm going to do my next one in red. This one is plus 3 minus 1. Let me close up my brackets. When I simplify this, I get 16/3.